Okay, we can continue with our class. So the second example, we see that from the equation 1, we have two arbitrary constants, which is a and b. That means we are going to differentiate this problem twice. So the first derivative give us this, the y, the x, to be equals to, when you differentiate x squared, you have 2x, then the constant a. When you differentiate bx, you have your b. So from here again, you differentiate again because of the arbitrary constant that is 2. So differentiating again, this a will be gone. Then you have 2a. Yb is constant, and when you differentiate constant, you have 0. So you have this. Now, substituting this 2a into our equation 1, into our equation 2. So we have it to be this. The y, the x is equals to, instead of writing 2a now, we write this equation 3. We substitute equation 3 into equation 2. So we have it to be x d square y over the x square, then plus b that we are having here before. So after that, we make our b the subject of the formula for us to be able to substitute it here, that is eliminating it. So our b to be equals to dy dx minus, taking this x and this derivative to the left hand side, we have d square y over the x square, then x. So from this equation 3 that we are having before, we can look at the equation 3. We have this before. So making our a as subject of the formula to get a value for a also. So we have our a to be half of d square y all over the x square. Now we have a value for our a, we have the value for our b. Substituting it into the original equation, which is the equation 1, so we have this, y to be equals to this, a and b is being substituted here. So combining these expressions, that is, when you multiply this x that we are seeing here by the bracket, when you open this bracket, you have equation 6. So after the equation 6, so we realize that we can factor out d square y over the x square, d square y over the x square. So bringing them together, we have this equation 7, which is which is bracket of x square over 2 minus x square all over 1 d square y over the x square, which is our equation 7. So finally, when we take the LCM of this, what is inside the bracket, taking the LCM, when you simplify it, you have it to be x dy dx minus x square over 2. That is what you have in the bracket, is just x square over 2. Then you attach this multiplication, which is d square y over the x square. So all the methods are that is, the number 1, you count the arbitrary constant, you differentiate in the number of the arbitrary constants, you eliminate your constant. After eliminating your constant, then you form a differential equation. So let us look at the example number 3 and see. And example number 3 is a trigonometry example. We have our y is equals to a sine x plus b cos x as our problem. As we said earlier, we are going to count the number of the constants we have. And here also we have 2 constants. So you differentiate this problem in the number of constants you are having. So the first derivative, when you differentiate the y dx, you have it here. When you differentiate sine x, it's going to give you cos x. Then you put the constant. But when you differentiate cos x, we have negative sine x. That is why the sign is changing from positive to negative. So we have this to be our first derivative. Then second derivative, we have it to be when you differentiate cos from equation 2, you have negative sign. You can see that it's having negative now. Then you bring down the negative. When you differentiate sine x, you have your positive cos x, which gives us our equation 3. So now, how do we eliminate the a and b? So now when you notice this second derivative, you realize that this second derivative and the problem given, that is the first equation that we're having, we see that they are the same thing. The only difference is just the sign. So therefore, d square y over the x square that we're having in our equation 3 is equals to minus y from our equation 1. Since they look alike, you just only factor out the negative. Then you have the positive inside it. So you have our minus y. Then from here, we make our y, if we like, to be the subject of the formula, or you add y to both sides. Adding y to both sides will give us our differential equation. So these are all what we explained to each other last week. So today we are starting from initial value problem, and we start from the introduction. So differential equation often have infinite solution. So we said this in our first class. So we have infinite solution. It's now left for you to check which is the appropriate method I'm going to apply into this very problem given to me. So to choose a specific solution, additional information is needed. So what are the additional informations? So you can be given initial value problem to solve the problem given to you, which we are going to see today. So initial value problem, IVP. So a differential equation with one or more initial values is called an initial value problem. When we come to the application, so we understand all these points more better. So the number of initial value required equal the order of the differential equations. So what this statement is saying is that when you are given a first order differential equations, so the initial value problem that will be attached to that first order differential equation is just only one. When you are given second order, the IVP that you'll be having will be 2. When you're having third order, the IVP you'll be having will be 3 up to the nth order. And the IVP that will be attached to the nth order is what? Nth IVP. So that is what this is saying. If y prime is equals to 2x, an initial value like y of 3 is equal to 7 is needed. So this form a differential, or this form a first order initial value problem, as I just said earlier. So number 4, second order example. When you are given a problem, I have explained this also, when you are given a problem that is second order, the IVP that will be attached to it will be 2. And as you can see it, you have y of 0 is equals to 2 and y prime of 0 to be equals to 1, and so on. So together with the differential equation, it forms a second order initial value, so which is this. So after using this y of 0 equals to 2, then you differentiate the problem given to you, that is the initial problem. After differentiating it, then you now substitute this y prime of 0 to be equals to negative of 1. Number 5, we have notation. Often, the independent variable represent time. So as we are seeing this, when we come to the number 4, where we have y of 0 is equals to 2. So what this is saying, that 0 there is referring to what? Time, and is our independent variable. Y2 that we are seeing here is These 2 belongs to the y, which is our dependent variable. So let us quickly verify this. Verify that y is equals to 2 exponent raised to the power of minus 2t plus exponential t is the solution to y prime plus 2y is equals to 3 exponential t. This is the problem given to us with the IVP of y of 0 is equals to 2. So how can we solve this? This is a problem. So and we are giving initial value condition to substitute inside it. So now the solution, we start with the differential equation, that is this y prime plus 2y is equals to 3 exponential t. But to solve this, you are going to use this problem given to you because you're having a derivative here, and you are required here now because you want to find a solution to it. So you are required to find, as in to substitute y, and you are given y already, but you don't have your y prime. So to get your y prime, you need to differentiate this, and differentiating this, you have it to be, when you differentiate exponential minus 2t, so the minus 2 will come down to multiply these two to give us negative 4 of what we are having inside this bracket. This is the derivative. That is the y prime is equals to negative exponential minus 2t plus exponential t. Because when you differentiate exponential t, you still have your exponential t. Then plus 2 that we are having here. So the 2 that we are having here, then y, we are giving y already, and look at it inside the bracket. So expanding this out, we have this next step. So when you look through it, because I have already stopped it, I have already solved it, I solve it down step by step. So when you go through it, it's very, very easy to assimilate. So when you open this bracket, you have this. Then when you cancel out this negative 4 and this positive 4 that we are having here, so then you had what you are left with to give you 3et. And this verify what we are having here, because what we are having here before the substitution is y prime plus 2y is equals to 3 exponential t. So, and that is exactly what we have. But this question is giving us IVP of y of 0 to be equals to 3, and is yet to be substituted. So you now go to the initial problem given to you. You now substitute the IVP that you have in there. And from the IVP, as I explained earlier, this bracket, what is inside the bracket, is always your independent variable. And the independent variable we're having here is t. So that 0 belongs to t. When you substitute the t here into the initial problem, so you have it to be what I'm having here. Then after everything, substituting the independent variable, which is 3 from our initial problem. So you now realize that 3 is equals to 3. So what I'm saying, this exponential raised to the power of 0 will give you 1. This exponential raised to the power of minus all these will also give you 1. So that 2 times 1 will give you 2 plus 1, and you have it to be 3. So thus, the given function satisfy the initial value problem, because the answer of this gives you 3, which is what you're having here. So the second example is this. A baseball is thrown upward from a height of 3 meters above Earth's surface with an initial velocity of 10 meters per second and the only force acting on its gravity, so the ball has a mass of 0.15 kg at Earth's surface. Find the velocity of the baseball at time t. So what is its velocity after 2 seconds? So what we are only trying to explain to each other here is just how to substitute initial value condition. So from this question, so we have the differential equation to be given as this, that is change in velocity to be equals to negative 9.8 from, that is 9.8 for, that is our gravity. So we understand this already from our physics. Then from the question, the initial condition from our question is, the initial condition is, that is velocity of 10 meter per second. So it's 10 meter per seconds. Now, how do we do that? You do this by eliminating this change in velocity. And how can you do that? That is the integrating both sides. When you integrate this side, you have velocity of t to be equals to, when you integrate negative of 9.8, so a constant of t will be added. That is the constant of t will be added, then plus the arbitrary constant of c, that is the constant of integration. So to solve for c, we substitute t to be equals to 0 and v of 0 to be equals to 10, given from the equation. That is the velocity, the initial velocity that is given from our equation is equals to 10. So then the independent variable, which is the t, so is 0. When you substitute it, you have v of 0. Oh my God. So you have v of 0 to be 10 and is equals to negative of 9.8 of 0, that is the t, from multiplied by 0, you have 0. Then c will just be equals to 10. And the velocity function is equals to v of t is equals to 9, that is the initial problem given to us from this place. From this yield v of t to be equals to negative of 9.8t plus c. So from there, when you substitute the value of this c back, we have our c to be equals to 10. So when you substitute it back, you have, what is this? That is, therefore, when c is equals to 10, so our velocity will be equals to negative of 9.8t plus 10. So then the second question asks us to find what is the velocity after 2 seconds. So substituting this, which is, instead of v of 0 now, we have v of 2 after 2 seconds. So to be equals to 9.8 t. So instead of putting t, now you put multiply by 2 plus 10. Then is equals to, when you add everything and you multiply everything here, you have negative 9.6. So all these things, they are just something I have already break down. When you go through the slide, so and you follow the step one after the other, so you must arrive at the same answer that I'm having here. Okay, so the next slide. Now we are going to solution to differential equation. Substitute our IVP into our given problem. So now, solution to ordinary differential equation. So a solution to the ordinary differential equation, this refers to a function or a set of functions So when substitute into the differential equation, satisfy the equation. In other words, a solution to an ordinary differential equation is a function or a set of functions that make equation true. So what this is simply saying is this. So in a situation whereby you have in our basic mathematics, where you have x, okay, let us continue. So there are different type of solutions to ordinary differential equation depending on the nature of equation and any given initial or boundary condition. So here are two broad categories. So as this course is concerned, so there are many solutions of ordinary differential equations, but for now we will only be focusing on two, which are the general solution and the particular solution. So what is the general solution? The general solution of an ordinary differential equation represents a family of solutions. When we say general, so that means a family of solutions that include all possible solutions to the equation. It typically involves an arbitrary constant, which is all the difference between the general equation and the arbitrary solutions. So in the general solutions, you'll be seeing the arbitrary constant attached to it. Why the particular solutions, what you'll be seeing there, you'll be seeing an initial value problem will be attached to it. When you solve it, you'll be having a particular, a single answer. So as I was saying, it typically involves arbitrary constant and specific value of these constants are determined by additional conditions such as initial value or boundary value. While the definition of a particular solution is a solution or is a specific member of the general solutions that satisfy not only ordinary differential equations but also any given initial or boundary value conditions. The particular solution is obtained by substituting specific value for the arbitrary constant in a given general solution. I have already said this earlier. So the difference between the two is that for the general solutions, you'll be having arbitrary constant attached to it, while for the particular solution, you'll be having an arbitrary constant attached to it. So when we solve this, I think we understand it more better. So let us look at this general and a particular solution. So for this, we have dy dx plus 2y to be equals to 0. So we are going to solve this general solution. So how can we do that? As we have said earlier, ordinary differential equation have many methods. It just depends on the solver. So for this very simple equation, we are going to separate the variable. We'll talk more extensive on it in today's class. That is the separation of variable. We still have it. But to solve this, we have to separate the variable, that is taking this 2y to the other side to have minus 2. So after having minus 2y, then you divide both sides by y. So dividing both sides by y, you have it to be this, the dy over y to be equals to minus 2 that you take to the other side. Then the x, that is when you cross multiply, the x will come to this. So when we come to the separation of equation and of variables, so we explain this more better. So after separating variables, that is after y into one side, x into the other side, then you integrate both sides. So when you integrate this side, you have integral of 1 over y dy is equals to integral of negative 2 dx. So integral of this will give us ln y because it's an inverse. And when you have inverse integral, so the answer is always ln of absolute value of the denominator. then is equals to, then the integral of the x will give us x. You attach it to the -2, then plus c, that is the constant, that is the integration constant. So then you exponentiate the both side. When you exponentiate the both side, the exponential will go away with the ln. You have only absolute value of y to be equals to absolute value of all these. Exponential of all these, since you are exponentiating the both side. So you have it to be this. Now, using our indices or applying our indices, we can break this to be absolute value of y to be equals to exponential of c1 multiplied by exponential of negative minus 2x. Then the final answer will now be, when you go away with the absolute value, you have y to be equals to all this, the exponential c1. So we've let it to be c, since it's already constant, so you can represent it with only a single constant, which is c2. Then exponential minus 2x. So after solving this, what we just need here is that after this our y, after making our y subject, we still have our arbitrary constant, and this implies a general solution, because we said that a general solutions will always have arbitrary constant attached to it. So let's see the particular solution. So let's say this, from this problem given to us, that is from these solutions that we have from our general solutions. So let's say we have an initial conditions. We said it earlier that solving particular solution, you must have initial value condition attached to it. So now let's say that the initial value condition of this is y of 0 to be equals to 4. So we can use this condition to find the particular solution. So y of 0 to be equals to this now, to be equals to what we are having before. And y of 0 to be equals to 4 simply means what? The independent variable, which is x, is 0. Y, that is the dependent variable, is 4. So when you substitute x to be 0 from this exponential, you have it to be x raised to the power of 0, then multiply by the c. Then, since our dependent variable is 4 from the IVP, so you substitute it, then we have our c to be equals to 4. So when you substitute this 4 into this general solution you are having before, then you call it a what? You call it initial value problem. Sorry, you call it a particular solution, because you have already eliminated the constant given to you, the arbitrary constant given to you with the help of the initial value problem. So let's look at the next slide. So the differential equation, so we are still on the general and particular solution. So let's see this. From the graph that we are having here, so we can see the graph with many curves. So, and this is talking about a general solution, that a solutions that will always look alike. Why the particular graph, we don't have it here, but from the name particular, it means you have to have only a specific either curve or a straight line. It depends on the equation. If it is quadratic, you have it to be curved. If it is linear, you have it to be straight line, and so on. And if it is sine, so we know how a wave is. So that is the form it's going to take in the graph. So now the differential equation y prime is equals to 2x has multiple solutions. Has a multiple solution such as y is equals to x squared and y is equals to x squared plus 4. So what this is saying is that when you have y is equals to x squared, and you have y is equals to x squared plus 4, and you also have x squared, y is equals to x squared plus c. All these, when you differentiate them, you still have the same thing, because what is attached to them are constant. You have here, you don't have any constant, the constant is 0. Here the constant is 4. Here the constant is c. And when you differentiate constant, it will be 0. So y derivative is equals to 2x. That is when you differentiate x squared. So that is what this is saying. So where c is is any constant, is also a solution, because the derivative of x squared plus c is always 2x, as I said. So in general, the solution to this differential equation are represented by the family of function. And what is the family of the function? This is the family. Y is equals to x squared plus c. This will always satisfy this y prime is equals to 2x, irrespective of what you have as your constant. So this is an example of a general solution with the graph. So let's take more examples on the particular solution. So find the particular solution to the differential equation y is equals to 2x passing through the point 2, 7. And when you have this type of pair, it means the first one is for what? Is for the independent variable, while the second point is for the dependent variable. So in a nutshell, 2 is for x, 7 is for y. So from the solution, when we solve this, we have y prime to be equals to 2x. So after having this, to determine the value of c, because you want to find a particular solution, not a general solution with a constant anymore. So substituting x equals to 2 and y to be equals to 7 into this equation and solve for c. So this, we arrive at this, y to be equals to x squared plus c, which is our initial problem. So substituting the value of x to be equals to 2. Please, we should not forget this. I explained this earlier, that when you are given IVP, that is the initial value problem or condition, so it depends on the number of order that you're having in your problem. Like for this now, you're having y prime, and y prime is first order, so you will only be having one single IVP attached to it. So that is why, and when you want to substitute it, you will not substitute it into the derivative. You will go back to the problem, that is the initial problem given to you. But when you are having a second order, you'll be having two IVP attached to it. Then you substitute one into the first problem, then the second one into the, when you differentiate the first problem given to you. So now, substituting these 2 into x, we have 2 squared plus c. And our y, that is the dependent variable, is 7 already from the point given to us. So 2 squared will give us 4. And when you take this 7 to the other side, we have our c to be equals to 3. So therefore, the particular solution passing through the point 2, 7 is equals to y square plus 3. Our 3 is from the c. So in summary, when we want to find a general solution to a differential equation, after solving everything, you realize that your solution is having an arbitrary constant. Why, when you are solving a particular solution, after solving everything, you realize that you are having a particular solution, that is a solution without arbitrary constant. So this is another example. Let's y equals to exponential of this plus 2x plus 3. So to verify that y is a solution to the differential equation of this. So you want to find out, I think we saw one of these before, but this is having an IVP condition. So you want to check that this problem given to you, that is the y, is a solution to this derivative, that is to y prime plus 3y is equals to 6x plus 11. When you substitute, that is when you substitute for this y prime plus 3y, are you going to have 6x plus 11? So let us see. Now, first of all, since there is prime here, you have to differentiate the problem, the initial problem. And when you differentiate the initial problem, when you differentiate exponential minus 3x, you have minus 3. You bring it down. Then plus, when you differentiate 2x, you have only 2. So when you differentiate constant, you have 0. Now, having y and y prime, we can now substitute it into this y prime plus 3y. Maybe we are going to have our 6x plus 11. So let us do it and see. And which is what we are having in this long bracket here. We substitute our y prime and we substitute our 3y. Look at it here. Opening this bracket, you have this. So after substituting them plus 9, 9 is not here because when you multiply, 9 is missing, I think, is omission. When you multiply 3 times 3, here you must have plus positive 9. So after having that, this minus 3 exponential 3x will cancel away this positive 1. Then you'll be left with only this. That is 2 plus 6x plus 9x. So when you add them together, think you should arrive at this 6x plus 11. So after your elementary mathematics, after applying your elementary mathematics, just opening the bracket, eliminating them. After eliminating them, so you must arrive at this 6x plus 11. Yeah, so that is the 9 that I said is omitting here. That's 2 plus 9 will give us 11. Then you have 6x already when these two cancel out. So having this, when you find the derivative of this initial problem and substituting it into this differential equation, and you still have your 6x plus 11, so that means it's a solution to the differential equation. So this is the same thing. This is also what I explained earlier. I just try to solve it here step by step. So solution to ordinary differential equation. To solve a differential equation, we'll be saying this. You can follow this. These are the general steps. So each particular one is having their own steps, like the formation of the differential equation we talked about earlier, and the one we yet to talk about. They all have their specific steps in solving them. But this is just its general steps for all, and there are just 5 of them that we're having here. So determine the type of differential equation, either ODE or PDE. Number 2, identify if the equation is linear or non-linear. You check that also. So find a general family of solution. So using an integrating factor or other techniques. Then number 4, determine the value of an arbitrary constant in the general solution. Then the last one, if an initial value problem is given, find a particular solution that satisfies the given solution. So we've been applying all these. So in our problems, we still applied it as far as the ordinary differential equation is concerned, these are the steps we'll be using, the general steps we'll be using. So now, separation of variables. When we say separations, literally, we understand it to mean to just spare aside, to separate things, to put aside two different things. Before you can separate anything, so that very things must be more than one. So anything that is more than one, so you can be asked to separate it into different part or into different side. So method of separation of variables is one of the most widely used techniques to solve differential equations or partial differential equation or differential equation, anyone. It is based on the assumption that the solution of the equation is separable. That is, the final solution can be represented as a product of several solutions. So this is what I'm saying. Before you can separate anything, so this is the general format of how you see it. That is, u of x of comma t to be equals to x of x and t of t. So you see it, you must see it in this general format. So then the general form of the separation of variables is written in this way. That is, f of y dy plus g of x dx to be equals to 0. So when you notice this, you see that the y are together in one side, while the function of x and the x is also together in one side. So even when you take this g of x to this side, it's still not going to affect anything. So that means you separate the variable. So after separating the variable, so such equation can be solved by integrations. I think I talked about this in our last class. So you differentiate it where C is an arbitrary constant. Let us quickly look into the example we have here. So solve the differential equation dy over dx is equals to 2xy. So from here, the independent variables is x, but is attached, is interacting with y. That is, at the right hand side, we have x and y combined. So how can we separate them? It's just very easy. It's what we've been doing in our subject of the formula. That is the prerequisite of this. And in our variation, in our basic mathematics. So from here now, to separate this variable, you said what? You multiply the x to both sides. When you multiply the x to both sides, so you'll be having only the y here at the left hand side. So when you have your dy, you've not separate the variable, you still have y by the other side. So how can you go away with the y now? By dividing both sides by y. So when you divide both sides by y, you have dy now over y to be equals to 2x dx. Now you separate the variable. You're having the y term in one side, you're having the x term in one side. Now after separating it, the next step is integrating both sides. So when you integrate both sides, you have it to be this. That is the next step here. After having this or having this, the integral of 1 over y is ln absolute value of y. We know this in our integration. The inverse of integral will always be what? Absolute value of the denominator. Then the integral of of dx, integral of, okay, x is missing here. So integral of x dx will give us what? X squared all over 2. Where that 2, the denominator here, we cancel these 2 that we are having here. Then we have ln absolute value of y to be equals to x squared plus c. So you take the exponential of the both sides. When you take the exponential, you have the next step you are having here. So after that, this exponential go away with the ln, you have only y. Then the exponential of this, when you apply the indices, you have it to be this. That is exponential of c multiplied by exponential of x squared. To have your ordinary y, which is the last step, you must make your y the subject of the formula after all these steps. So you have our y. When you want to break away this absolute value, you have positive and negative at the other side. Then this exponential c is our constant. We can represent this with a single constant, which is k, and exponential of x squared. So this is just a simple way, or this is just a simple problem. And as you know, mathematics, you start from simple to complex. So let's go to the second problem to see what will happen. So this was a problem. We have find the general solution to x squared plus 4 dy dx to be equals to xy. This a mix-up of interactions of variables. So how can we separate the variables? You first of all, you sit down, you observe them very well. So observing this now, the simplest way, you can cross multiply. When you cross multiply, this dx will come back here. And when you have your dx up, you have dy now at this side. The x has gone to the other side. Then the y, x squared plus 4 to be equals to xy dx at the other side. So you still have your y at the left hand side. What do you do again? You divide both sides by y. When you divide both sides by y, you have the next step you're having here. Then after that, you want to take all x function or x variable to the other side. So you divide both sides again by the bracket of x squared plus 4, and you have dy over y to be equals to x all over x squared plus 4 is equals to dx. So integrating both sides, when you integrate both sides, just like what we did earlier, you have it to be ln of y, then to be equals to 1 over 2 ln of x squared plus 4, then plus constant of the integrations. So just like what we explained earlier, when you take the exponential of the both sides, you have your ln to be gone. Then you have absolute value of y to be equals to exponential. Someone wants to join. So, as I was saying, you have our absolute value of y to be equals to exponential of all these sides. Applying our indices, so we have exponential of c1 and this. So this very slide is explained explicitly in the next slide. Let me just open the next slide. So you see that the equations are the same. So this is what I'm saying. So integral of 1 over y dy and integral of x all over x squared plus 4 dx. So integral of 1 over y will give us ln y plus c1, that is the integral constant, while the integral of x over x squared plus 4 cannot just be ln x squared plus 4. You have to apply some techniques by letting the denominator here to be what? To be u. So u to be equals to x squared plus 4. Then the u, now the x, will give us, when you differentiate x squared, you have 2x. Then making the x subject of the formula, because you have to substitute back the x. So the x will give us what? The u in this back, we have our integral of x over x squared plus 4dx. So instead of this, we now have it to be what? 1 over 2 integral of 1 over the u, because our u is the same as x squared plus 4, then the u. So integrating with the respect of u, we have 1 over 2 ln u plus c2, that is the integration constant. Substituting back our u, we have 1 over 2 ln x squared plus 4, then plus c2. So the next step, we have our ln y already plus c1 in this side, then plus 1 over 2 ln x squared plus 4, then plus c2 at the other side. So exponentiating or exponentiating the both sides, we have ln, we go away with exponential. We have only our what? Our absolute value of y to be equals to exponential of the right hand side. So exponential of the, and don't forget this. So exponential of the right hand side will now give us this, which is applying the indices with the power. We have exponential of this and exponential of constant. So exponential of constant can be represented with only a single constant, because constant is always a constant. And as I told you, arbitrary constant, they are constants you attach to an equation that will not make any effect on it. So this we can use this c. Okay, we can use this c to represent this, to have absolute value of y to be equals to c. Then when you go back to this, so elementarily, when you apply your law of logarithm, so you realize that you'll be having x squared plus 4 raised to the power of half, and anything raised to the power of half, you can just simply write it as what? As the square root of that very thing. So which will give us absolute value of y to be equals to constant square root of x squared plus 4. So when you want to crash away the absolute value, I said it earlier, the other side you have positive or negative of what you're having here. So which is the general solution. Why is it called general solution? Because it's attached with arbitrary constant. So these questions from this slide is what we break down here. So you can see now when you go through the step, no step is missed or is missing. So when you go through them, so just write them down, practice them. Is very, very straightforward. So let's take another example. So the next example, we want to solve differential equations of this fraction. But here we are having an initial value problem with dependent variable equals to 2 and independent variable, which is x, to be equals to 1. So let us see what will happen. So now our first step from separating variables is that you find a technique of separation of the variables you're having, so that y will go on one side and the x will go on the other side. So now, when we cross multiply, the x will come back to this side, as we have, as what we used to do, as what we have here, that is this therefore. So the x will come back to this side. Then multiplying y to both sides, you have y dy to be equals to negative of x, then the x, which is what we're having. So after separating the variable, the next step is to integrate the both side. So you integrate the both side, integrating y dy, you have y squared. So integrating y dy, you have a y squared all over 2 plus the constant. Integrating negative x dx, you have x squared all over 2 also, then plus the arbitrary constant. So now y squared is now equals to, that is when you multiply 2 to both sides, multiplying 2 to both sides, you'll be left with y squared to be equals to negative x squared plus 2c. That is the 2 from what you multiply to both sides. So this implies what? Y squared to be equals to minus x squared, then plus 2k. 2 plus c, we represent it with k as one constant. Now, substituting the IVP into the given problem will give us x to be equals to 1 and y to be equals to 2 into equation 1. So then when you substitute this is the equation 1, where you are having your y squared is equals to minus x squared plus 2c. So when you substitute your 1 and 2 for y, so you arrive at this y to be equals to square root of 5 minus x squared. So it's just very simple. Just substitute x to be 1 and substitute your y to be 2 from this very equation. Y squared is equals to minus x squared plus 2c. Or you use the up one, y squared over 2 to be equals to x squared over 2 plus c, anyone you use. So you arrive at this very solution. So another exponential problem under this, which will be the last example under the separation of variable, is this. Solve the differential equation y prime is equals to exponential of x minus y. So we still follow the same methods we're using. So we have y prime to be equals to, y prime is the same thing as writing dy dx to be equals to exponential of x minus y. So using our indices, this is simply dy over dx is equals to exponential of x all over exponential of y using our indices. This is very familiar to all of us. So after this, we can cross multiply to separate the variables. So when you multiply both sides by dy dx, you arrive at this exponential y dy is equals to exponential x dx. So after having this, after separating the variables, then you do what? You integrate both sides. So integrating both sides, you have this integral of this and integral of this. And whenever you integrate exponential, any exponential, so you still have that. You have you still have exponential x, will still give you exponential x, but over 1, because you have to differentiate the power. then divide it by it. But here, since we are having the power to be 1, so the integral of exponential x is equals to exponential x over 1. So the x. Then the same thing happens to the exponential of y. When you integrate exponential y, you have exponential y over 1 plus c. So taking the natural log of both sides, that is ln exponential y ln exponential x plus c. So cancel away the ln, will go away with the exponential. You have the absolute value of your y to be equals to exponential of ln x sorry, when you exponentiate the both side, so the exponential here will go away with the ln in the right hand side, and taking the exponent of the left hand side, you have exponential of all what is here. So we've been applying it in our previous example. So when you write them down in a paper, you go through them, you will realize that all these are very straightforward and they are very simple. And it's very, very important for you to understand the concept as we are going. We've talked about how to formulate a differential equation. We've talked about how to apply IVP, the initial value problem. We've talked about the general solution and the particular solution. Now we've talked about separation of variables, how to separate variables. So the steps that involve after your initial problem given to you, you separate the variables so that x will go to one side, y will go to one side, or it depends on which variable given to you. They can be given, you can be given x, t, you can be given x and z, and so on. So your aim is just to separate the variables. After separating it, then you integrate the both sides. After integrating the both sides, you take the exponent of the both sides, you apply some your log previous knowledge, some indices to arrive at just a single y, that is making a y a subject of the formula. So now the next thing we are going to talk about in today's class, although we are going to start this and give only one example, so the other examples is going to fall in our next class, and it's nothing but the linear differential equation. So all these rules and the form that each equations or solution or each problem is looking like, so are something you have to have to vividly study them, or vigorously study them, have them in your mind, that whenever you are seeing this form, it means this. Whenever you are seeing this form, it means that. So now, a linear differential equations take this form: dy dx plus p of x multiplied by y is equals to q of x. So anytime any differential equations take this form, that is y prime plus p of x times y is equals to q of x, so don't even bother yourself, it's called a linear differential equation. So they are solved by finding an integrating factor and integrating both sides. So you must go back to your integration, either you like it or not. Study them very well, because these are all what you'll be applying in this differential equation. So these equations are fundamental in modeling dynamic systems across diverse fields. So steps to solve linear differential equations. So as we have been having it in our previous discussion, steps in solving this and that. So likewise, this linear differential equation also is also having steps in which you take in solving them. You can't just solve a differential equation anyhow you like. You first of all, you observe the form in which it takes. After observing it and understanding the forms, then you now apply the necessary steps and the sufficient steps that is required for it. So now the first steps, identify the coefficient. So that is the coefficient of P of x and Q of x. You must identify it from your given problem. That is, when you are given something like this, dy dx plus P of x times y is equals to Q of x. So you must find the coefficient of P of x, that is the y. The coefficient of Q of x also is very, very important for us to find. So number 2, find the integrating factor. Here, you must find what they call integrating factor. And what is the integrating factor? Is also what you are seeing on the screen here now. That is the integrating factor, the function of x, is equals to exponential of integral of P of x dx. You first of all, you solve this. After solving this, then you keep it as your integrating factor. So we have the next step to express as derivative of product, which is what we are having here. So these are just steps. When we come to the application, we will understand them very, very much better. So number 4, integrate both sides. So when you integrate both sides, you have this. Then the next step, which is the final step, solve for y. So that is solving the resulting equation for y. And what is always the resulting equation? This is where you apply everything. The integrating factor, the p of x, you need the p of x for the integrating factor. Then the q of x have surface here. So y is equals to 1 all over integrating factor of integral of q of x multiplied by integrating factor dx plus c. So this is the general form. So when we come to the application, we take only a single example. So from this example, you'll be able to understand it, as I said, how to solve a linear differential equation. And we won't able to take more than that one example. So when we come next week, we solve more examples, then go to the next in our content or in our syllabus. So let us check this. Given linear first order differential equation of this, now we have a problem. dy dx plus 2y to be equals to 2 exponential x. So as I said, number 1 thing that is important in solving differential equation is inspecting. You have to inspect what type of questions am I giving. So what type of form does the question take? And for this now, having this, we see that is linear differential equation, because we have our 2y that look like this, that look like our what? P of x, y. Then we have that 2 exponential x that it look like our what? Q of x. Okay, so having that, we identify our P of x from the step. Then our P of x is equals to 2 from this question. Why our Q of x is equals to 2 exponential x. So the next step is finding the integrating factor. And the integrating factor is having a formula, and the formula is exponential of integral of P of x, and our P of x is 2. So substituting this into the P of x of our integrating factor, we have exponential of integral of 2 dx. When you differentiate 2 dx, you have only what? You have 2x. that is the integral of 2 dx. Yes, you attach x. Now, what is the next step? Multiply both sides by the integrating factor. And what is the integrating factor? You have it now to be exponential 2x dy dx plus 2 exponential 2x y to be equals to. So now you are what? You are multiplying the integrating factors to both sides. So after that, you come to the next step, that is express the left side as a derivative of a product. Derivative of a product, that is what we're seeing here. D dx of exponential 2x y then is equals to what you are having before. So that is expressing only the left side as the derivative of product. So you have this. Now, integrating both sides, what are we going to have? You integrate the derivative of a product you have in your previous step and what you have in your right hand side. Integrating that integral, we go away with this d dx, and you'll be having only what? Exponential 2x multiplied by y to be equals to integral of what you're having before in your left in your right hand side per se, in your right hand side. Yes. So after that, the last steps, as it was explained from the step that we must take. So the last step is finding the what? Finding the y. And the y is what encompasses all what we've been substituting since, that is the p of x, the integrating factor, the q of x, and so on. Okay. So simplify further, that is, these are our y. Please a minute. Yeah. Just a minute, please. I'll do it. Okay. So sorry for keeping you waiting. Okay, as I was saying, after finding what your p of x is, and from here we said our p of x is equals to 2, q of x is equals to 2 exponential x to the power of x. Then we find our integrating factor to be what? To be exponential x. Yes, exponential 2x. Now, having all these, we must to substitute it into the general formula that I just showed us earlier from the steps. Yeah, this formula, that is y to be equals to 1 over integrating factor of integral of q of x multiplied by integrating factor again dx plus c. So now, how can you substitute that? You have 1 all over, what's our integrating factor? Our integrating factor, we find it to be exponential 2x. Then into the integral of what's our q of x? Our q of x, we find it to be, from the equation given to us, is 2 exponential x. So 2 exponential x. Then the integrating factors give us exponential 2x. Then the x you're having from your formula, then plus the constant of integration. So there is one very important thing we need to note here. So it's only this general form where you have your y here that you plus the integration constant. You are not going to plus it when finding your integrating factor. Just because we said whenever you integrate, you must add a constant c. No, you will not add anything when finding your integrating factor. You only add it when you want to substitute it in the general formula. So substituting it in the general formula and doing your little arithmetic, so you realize that when you integrate exponential 2x plus times 2 of exponential x again, dx. So you have exponential x and you have exponential 2x. Using indices, these two can give you exponential 3x. Then 2 is a constant. You can take it out the integral. When you take it out the integral, you now be having 1 over integrating factor, which is exponential 2x of 2 integral of exponential 3x dx plus c. Then when you now integrate exponential 3x, as I said earlier, you differentiate the power of the exponential. And when you differentiate the power, you have 3. Then you divide it by what you're having. So now you have y to be equals to 1 all over exponential 2x 2 integral, yes, of what you're having, 2 integral of exponential 3x dx. Now, these 2x can cancel 3x here. We'll be left with only exponential x. So, now, the final answer to this will now be what? Y to be equals to 2 all over 3. That is 2 from the behind integral, then the 3 from when you integrate exponential 3x. So you now have it to be constant of 2 over 3 exponential minus 2x times exponential 3x. Yeah, exactly. Exponential 3x. So applying your indices here, as I said, you will be left with only what? Exponential x, because minus 2x and minus 2x plus 3x. Yes, you'll be having only a positive x. So this implies that you'll be having exponential of x. So our final answer, as I said, will be y to be equals to 2 all over 3 exponential x plus c. So plus c exponential minus 2x because this minus exponential minus 2x, you must multiply it through the bracket. Yeah, through the bracket of both the constant and what you are left with, that is the exponential x. So in generally, you have it to be y to be equals to 2 all over 3 exponential x plus c, which is the constant, exponential minus 2x. So that will be the end of the class for today. So we've been able to take a summary of our last class. After the summary, so we started our today's class from uh, formation of differential equations. So after that, we come and talk about the initial value problems and how to apply it. Then after this again, we talk about the general solution and a particular solution, where we say that the difference between the two is that the general solutions, we always have a constant, an arbitrary constant attached to it after the solution. Why the particular solutions, we eliminate the c. And how can we eliminate the c? That is by, we'll be given IVP, initial value problem, after solving it. So you have a single solution. So we show ourselves a graph of a general solution. So this is general solution. So you'll be having it. The only thing is that there will just be what? There will be smaller. They will be smaller than each other. But all this is general solution to a particular problem, as I showed you earlier, from the y prime, from y is equals to x squared. So that we say that is the same thing as having y is equals to x squared plus c, or plus 4, or plus 10, or plus any number behind. So provided it's constant, and differentiating constant will be equals to 0. So from there, we talk about the separation of variables. Then the last one, we talk about how to solve linear differential equations. So which is where we stop. So all these things that I'm just saying that looks like abstract to you, just go through the slide. I already break it down, and I ensure that I solve them step by step. No step is missing. So when you see a step that is missing, that is, you should check yourself. You have to go back to the uh, elementary work. So that is what I'm just left with. That is the indices or the logarithm. So and so on. So get a paper, write all these examples down, practice them, and you know one logic thing about mathematics is that so the instructors will always solve, maybe as they used to say, a simple question in the class. So then they'll give you a tough one when it comes uh, to the problem set. So, but there's nothing hard in all this, rather than you have to put all these things into practice. Your consistency, your hard working, your determination, focus is all what you need to understand these mathematics or these ordinary differential equation. So get a paper, write them down, solve them, go to the recommended textbook, take more examples, solve it, go to online, so check more examples and solve them. So this will be the end of today's class. Thanks for listening.
Thank you very much, sir.
Thank you very much. We really appreciate it. But we
Yeah.
need a PDF of the handbook.
Okay, thank you. I actually enjoyed the lesson. It's quite good. At least it
Come
clarified
again.
so many doubts I had. I enjoyed the lesson because it was quite good. It clarified some little doubts I had when I read the textbook. But one question I want to ask is your